Good afternoon, students. Welcome to my lecture. Today I am going to discuss about binary search trees. In previous class already I have started right definition and why we require binary search trees. In previous class I had discussed right. Here see once again I will recap for 10 minutes. Just wait. Okay, let us see binary search tree. What is meant by binary search tree? See, binary search tree, actually, why we require this binary search tree means if you want to perform insertion operation efficiently. If you want to perform, okay, if you want to perform insertion operation efficiently and deletion operation, if you want to perform deletion operation efficiently and if you want to perform search operation efficiently, you require a data structure called binary. It is a non-linear data structure. You require binary search tree. Why you require binary search tree? To perform insertion operation efficiently, to perform deletion operation efficiently, and to perform search operation efficiently. What you require? Binary search tree. Coming to arrays, here insertion operation, deletion operation or inefficient. Okay, in array is also linear data structure. Here in in arrays, insertion and deletion operation are inefficient. Those are not efficient. Inefficient, it takes a lot of time to insert the element and it takes a lot of time to delete the element in arrays. And search, if you want to search an element in array, it is very efficient. That means you can easily search an element using, there are many searching techniques like linear search, binary search, Fibonacci search. There are many searching techniques, right? So using those searching techniques, you can easily search an element, whether an element is present in the array or not. Okay, now let us take linked list. Let us take linked list. Linked list. Here in linked list, insertion operation, deletion operation are efficient. You can easily insert an element at the beginning. You can easily insert an element insert a node, not element, insert a node at end. You can easily insert a node at middle. Okay, you know already the algorithms already we have discussed, right? So here, while inserting a node at beginning or while inserting a node at middle or while inserting a node at end, here you no need to disturb any elements or any nodes. Okay, simply you have to link the address. That's all. No need to disturb. Here, elements will not be disturbed. So insertion and deletion operation are efficient in linked list. Coming to search operation in linked list, if you want to search an element sequentially, here it is not that much efficient. Okay, it's not that much efficient as compared to the arrays. So here using linked list you can perform insertion and deletion operation efficiently, and coming to search operation, it is not efficient when compared with arrays. So you require some other data structure which is used for inserting efficiently, for deleting efficiently, and to perform search operation efficiently. What is that? Binary search tree. Using binary search tree, you can perform insertion, deletion, and search operation efficiently. Okay. Now let us see the definition of binary search tree. What is meant by binary search tree? Let us see it. Binary search tree. Let us see the definition. Here binary search tree, it is a binary tree. It is a binary tree. It is a binary tree with a property that the property What is that property? See here. All the elements less than node X will occupy as left child. Okay, all the lesser elements will be as left child when compared with some node X. Okay, all the lesser elements of node X will occupy as a left child. Next property, all the elements greater than node X will occupy as a right child. Now all the greater elements when compared with X, all the greater elements will occupy as a right child, will be as a right child of X. This is the property of binary search tree. Once again, see students, what is the property of binary search tree? All lesser elements will be as a left child of node X when compared with value of node X. And all greater elements will occupy as a right child when compared with node X. This is the property of binary search tree. Now, let us see an example. See, this is an example. What is the root node here? 25 is the root node. Now, see here, what I said, what is the property? All lesser elements than 25, all lesser elements than 25 will be as left child. See here, these are lesser elements, less elements than 25. See, 22 is less than 25, so it occupied as left child, and 20 is less than 25, so it occupied as left child. All lesser elements than 25 will occupy as left childs. So, or you can say like this, left subtree elements are lesser than root node 25. You can say like this. Okay. Now see here. Now right subtree. Let us take right subtree. Let us take this right subtree. See here. This right subtree, all elements in the right subtree are greater than which element? Root node 25, or greater than root node 25. So all the lesser elements will occupy as left childs, all the greater elements will occupy as right childs. Now let us take subtree. Now see here, let us take a subtree, this one. This subtree, see, this is a subtree, right? Now here in this subtree, what is the root node? 22. Now see here, 20 node is less than 22, right? See, I'm talking about this subtree. 22 node, see the 22 node. Here 20, this one, I'm talking about this. One second, I will erase it. I'm talking about this node. Now this 20 is less than 22, right? So that's why this node occupied as a left child. That's why you have inserted node 20 as left child of 22, because 20 is less than 22. All lesser elements will occupy as a left child. This is the property of binary search tree. Now let us take right subtree. One second. Let us take this right subtree. Now here in this right subtree, 35 is a root node. This is a root node. Now see here. See, all the elements left child. So okay, all the elements left of the 35 or less than 35, right? See here, 30, 32 or less than 35 only, right? That's why they occupied as left subtree, left children. Okay, next, let us take this one. Now let us take right subtree, this 40. See here, this is a root node. In this right subtree, in this right subtree, what is the root node? 35. Now see here, 40 is greater than 35, right? That's why it is occupied as a right child. All lesser element will occupy as left childs. All greater elements will occupy as a right childs. Okay, 40 is greater than 35. That's why it occupied as a right child. I hope you understood, students. Now let us see what are the operations. Once again, see this binary search tree. This is a binary search tree. What are the operations of operations? Write down. You need to note down running notes. Write down the example tree. Now see, what are the operations of binary search tree? First one is insert operation. Insert operation. Second one is a delete operation. Delete operation. Third one is search. Search operation. These are the operations of binary search tree. In your syllabus, they have given only insert and delete operation. I will explain search operation also. Here, these are the operations of binary search tree. What are the operations of binary search tree? Insert operation, delete operation, search operation. Students, is there any disturbance here? Another class is going on. Is it clear? My voice is clear? Is another voice is overlapping with this? As another class is going on here? Please respond, students. Haripriya, okay? No disturbance. Okay. If another voice is overlapping, just please inform me. Okay, it is clear. Okay, Harshita. Okay. Okay, see here. These are the operations of binary search tree. Now, here you need to represent, see how this tree is represented in memory. You have to use arrays or linked list. Okay, now let us take only linked list. A linked list representation. Here every node linked list representation. Here every node contains how many fields? You need to use linked list representation only, not array representation. You can represent this binary search tree in memory. How to represent this binary search tree in memory? You need to implement using linked list. You can implement this binary tree using arrays also, but we would like to prefer this linked list only. See, now each node consists of how many fields? 3 fields. Each node consists of how many fields? 3 fields. First field name is, one second. First field name is left. Left is a pointer which contains address of left child, or it points to left child. Next field is a data field which contains node element. Next field is right, which contains address of right child. Okay, this is the linked list node representation. Now let us see structure declaration. See, in examination also you need to explain like this only. First you need to write what is meant by binary search tree. Next you need to next you need to show an example, and then you need to write node representation, and then you need to write structure declaration, and then only you have to explain each and every operation. For example, in your examination, if they ask to write an algorithm for insert operation, first what you need to do? You need to write what is meant by binary search tree. Okay, next you need to write, you can write example like this example you can write, or okay, or you can skip it. After writing definition, you need to write node representation. After writing node representation, you need to write structure for each and everything. For stacks also you need to write node representation, structure declaration, all these things you need to write. Okay, what is the structure declaration? Let us see structure declaration. You need to use struct keyword. Struct keyword here, linked list, right? We are representing this tree in linked list. So structure name is node. Now, each node consists of how many fields? 3 fields. What is the first field? Left, which contains address of left child. So that means it points to node only, another node. So type is struct struct node. Left is a pointer. Okay, left is a pointer which contains address. Next one is, what is the next field? Data field, right? See, once again, see here, I'm drawing left, data, next. Now see here data is nothing but element which is an integer, so int data semicolon. Next what is the next field? Sorry, this is right. What is the next field? Right. Okay, right contains address of which node? Right child node. So type is struct node only. Struct node space star right semicolon, close the brackets. After closing bracket, see here, after closing bracket, you need to declare a structure variable. Why to declare a structure variable? Because if you want to access this left, and data and right, what is this left, data and right? Those are the structure members. If you want to access these structure members, you need to declare a structure variable. Where to declare a structure variable? After closing structure, root, see, star root semicolon. Now you can access the left, data and right like this: root arrow mark left, root arrow mark data, root arrow mark right. In this way you can access. I hope you understood, students. I will erase all these things. This is the structure declaration. Now let us see how to insert the elements operation. 1 second. Okay, 1 second, please wait. I will erase all these things. Now let us see operations of binary search tree. What are the operations of binary search tree? Let us see it. Keep the heading operations of binary search tree. Binary search tree operations. Let us discuss one by one. How many operations are there? Insert, delete, search. First, let us discuss about insert operation. How to insert? Students, I request all these students to note down step by step. You need to note down. In examination also, you have to write in step by step. And you need to explain each and every step, what you are doing in that step. Insert operation. Insert operation, keep the heading binary search tree operation. First one, insert operation. Insert operation. Now write down the example. Keep the heading insert operation and write down the example. Construct binary search tree for the following elements. Note down, please note down. Construct binary search tree for the following elements. This is the problem. What is the problem? Here these are the elements given. In examination also they will give in this way only. Construct binary search tree. Here you need to insert each and every element, or you need to construct binary search tree with the following elements. What are those elements? Write down the elements. 25, 35, 30, 32. This is the problem, okay? You need to solve it. What is the solution? You need to construct a binary search tree for the following elements. Let us see the solution. First, note down 25, 35, 30, 32, 22, 40 and 20. These are the elements given. Now, let us see the solution step by step. I request all the students to note down step by step. Solution. Step 1. Now, what is the first element? 25. Always remember, first element will be the root element. What is the first element given? 25. Write down 20. 1 second. 25. 25. Please note down like this. Inserting element, or like this. Inserting node 25. You need to write like this, or inserting element 25. You need to write. See, each and every step you need to explain. Here I'm not explaining like that. Just I'm drawing the diagram. But you need to explain like this. Step 1, inserting element 25 or inserting node 25, like that. Now let us see. See, always remember first element. What is the first element given? 25. 25 will be root element. 25 will be always root element. Now step 2. Next step 2. Step 2. Now what is the next element? See, first element 25 completed. Next you need to insert 35. Now where to insert 35? See, where to insert? See, 1 second. 25 is a root node. Now see, 35 is greater than 25. Remember the property. What is the property? All greater elements will occupy as a right child. All, 1 second. Are you listening? Okay. See, all greater elements will occupy as a right child. Here, now compare the 35. Compare 35. You need to insert 35. Now what is the next element? 35. Now compare with 25. Compare with 25. 35 is greater than 25. So here you need to insert as a right child. All greater elements will occupy as a right child. This is a step 2. Note down. Please note down step 2. Next, step 3. Next, step 3. Step 3. Now what is the next element? 30. 30, right? Note down the previous tree. Note down previous tree. Now you need to insert element 30. Always remember, you need to compare elements with root only. Come from root. Here you need to insert element 30. Okay. Here you need to insert element 30. Now if you want to insert element 30, you need to compare element 30 with a root node. Start from root node. See, 30. What is the root node? 25. 30 is greater than 25, right? 30 is greater than 25. That means greater means it will occupy as a right child. Come to right. But right side there is another element. What is that element? 35. You need to compare element 30. Here we are talking about, here you need to insert element 30. Okay. You need to insert element 30. So right side again there is another element. Again you need to compare element 30 with 35. Okay, compare element 30 with 35. 30 is less than 35. Right, see here. You need to insert element 30. Okay, compare with 35. Compare with 35. First you have to compare with always root node. 30 is greater than 25. So come to right side. Okay, greater elements will occupy right child, right? As right child, right? So come to right. Right side there is another element 35. Compare with 35. 30 is less than 35. Less means it will occupy as a left child. 30. Okay, completed. Insertion of 30 element is completed. This is the step 3. This is the step 3. Now step 4. Step 4. Write down the previous tree as it is. 35, 30 as it is. Write down. Now what is the next element? 30 completed. 30 completed. 32. You need to insert element 32. 32 you need to insert. Now if you want to insert element 32, you want to insert element 32. If you want to insert element 32, you need to compare, always start from root. 32, right? 32. Here you are inserting which element? You are inserting, write down like this, inserting element 32. Inserting element 32. 32. Compare 32 with 25. 32 is greater than 25. All greater elements will occupy as right child. Come to right side. There is another element, right? Come to right side. What is that element present? 35. You need to compare element 32 with 35. Here 32 is less than 35. See, compare 32 with 35. Here 32 is less than 35. Less than means All lesser elements will occupy as a left child. Come to left of 35. What is present left of 35? There is again another node. You need to compare with that node. 30. Compare 32 with 30. 32 is greater than 30. Greater means it will occupy as a right child. 32. This is the tree. Step 4. Is it clear, students? Should I explain it again? Please respond. Is it clear for you? Is the concept is okay? Clear for you? Shall I continue? Shall I continue? Shall I continue? Haripriya only responding. Remaining members, shall I continue? Students, up to now, is it clear for you? Is it okay? Concept is okay for you? Remaining members, are you listening? Only Haripriya is there in the class. Please respond. I'm asking you only. Jagadish, roll number 30. Jagadish, okay? Okay, I will continue. It's very, very easy, students. Now, step 5, right? 32 completed. What is the next element? 32 completed. Just wait. What is the next element? Yes, see. Oh, no, wait. Yes, 32 completed. What is the next element? 22. You need to insert element 22. Step 5, right? Step 5. Step 5. Note down the previous tree as it is. What is the previous tree? See, this is the previous tree. Note down previous tree as it is. 25. Next 35. Next 30. Note down previous tree. Previous step 3. Tree. Note down previous step tree as it is 32. Now what you need to insert? You need to insert element 22, right? Okay, this is the tree. Step 5. You need to insert. Which one you need to insert? Insert element 22 only. 22 only. Just wait. Yes, 22 only. Okay. Step 5. See, you need to write theory part like this. Insert element 22. Okay. Now, always start from root node. Compare element with root node. What is the root node? 25. Compare which element? 22. You are inserting 22. Now you are inserting 22. Compare with 25. 22 is less than 25. All lesser elements will occupy as a left child. All lesser elements will occupy as left child. 22 is less than 25. So, it will occupy as a left child of 25. I hope you understood, students. Please note down. Next, step 6. If you understand, do all the steps. Insert all the elements. Step 5 completed. Here only I will explain. In this step only, I won't write once again. But you need to write step by step. Previous tree, draw again. In another step, previous tree. In previous step tree, draw again. Now let us see step 6. Step 6. Step 6. Now, which element you need to insert? Let us see. 40. 40 element. You need to insert element 40. Let us see how to insert element 40. Always you need to compare with the root element only. What is the root element? 25. Now, here just I will write inserting element 40. Now, you need to always compare with the root element. What is the root element? 25. See, 40 is greater than 25, right? Greater than means it will occupy as right child. Come to right side. But here there is another element. What is that element? 35. There is another element 35 at right side. Again, compare with 35. 40 is greater than 35. Greater means it will occupy as a right child. Right 40. I hope you understood, students. In the same way, insert another element. What is the another element? 40 completed. Now 20. You need to insert element 20. First, write down step 6. I request all the students to note down stepwise. And you need to write theory part like this. Inserting element 40. Like that. Next, which element? 20, right? Next, we need to insert element 20. Now, let us, next step 7, right? Please note down step 7. Step 7, what is that step 7? Inserting element 20 only. Just wait, I will see. 20 only. Yes. Next element, what is the next element you need to insert? Element 20. Now let us see how to insert element 20. It is very easy. Always start from root node. What is root node? Element 25. You need to compare element 20. Which element you are inserting? Element 20, right? You need to compare with 25. Compare element 20 with 25. 20 is less than 25. Lesser means all lesser elements will occupy as left child. Come to left side. But there is another element. What is that element? 22. There is another element 22. So you need to compare element 20 with 22. Compare with element 22. Compare with element 22. Here element 20 is less than 22. Lesser means it will occupy as a left child. Less than 22. Less than 22 means it will occupy as a left child of 20. Sorry, 22. Left child of 22, because 20 is less than 22. Lesser elements will occupy as a left child. Greater elements will occupy as a right child. This is the binary search tree. This is the resultant binary search tree completed. You have inserted all the elements. Is it clear? Please note down. Any doubts, students, please respond right now. Once again, I will explain. This is very easy. You need to remember the property. What is that property? All lesser elements will occupy as left child. All greater elements will occupy as right child. You need to compare from root element. Is it okay? Is it clear, students? Shall I continue? Please respond. Shall I continue? Shall I continue? Shall I continue? Please respond. Is it okay, or should I explain it again? Binary search tree insertion. Please respond, students. Harshita, Shravanti. Okay. Haripriya, okay. Okay, students. Now let us see. Let us see algorithm. Let us see. This is the algorithm. This is very easy. See, this is the algorithm. Now here see, tree is a pointer. You are taking another pointer. I will zoom it. Please wait. See here. Tree is a pointer which contains address of root node. Here you are assigning root node address. Why you are taking another pointer called a tree? Because remember that root always points to root node only. You should not disturb root node. Sorry, you should not you should not move root. Root should always contain root node address only. So you are taking another temporary variable. What is that variable? Pointer. Pointer variable tree. Tree is a pointer variable. You are assigning address of root node to tree. Now tree contains address of which node? Root node. Now value. Value is nothing but it is a element to be inserted. Value is a variable which contains element to be inserted. Now let us see the algorithm step by step. Start. First one is start. Next. See, initially tree is null only. See, 1 second. Just wait. See, this is a structure. 1 second. This is a struct node. Struct node. 1 second. Int data. This is a structure declaration, right? Star right. Semicolon. This is the structure declaration. Here you are going to declare a structure variable. Now initially you need to make root as null. Root equal to null. This is a structure variable. Root equal to null. Initially root will be null. Okay. Initially root will be null. Now what you are doing? You are assigning root. You are assigning root to tree. Now tree contains null. See, tree is null. Null equal to null for the first time. Null equal to null. True. This is true for the first time. Here I am explaining algorithm. Please listen carefully. Tree is null. Null equal to null. This condition is true. If condition is true. When this condition is true, control goes inside if a block or if a body. What is present inside if a body? Allocate memory for node. Allocate memory for node, say temp. Now you need to allocate memory for temp using malloc. After allocating, what you need to do? You need to insert value. Temp of data equal to value. Value will be inserted in data field. Next, temp of left equal to null. Next, temp of right equal to null. This is what you are going to do after allocating memory for node temp. Next, after that, for the first time, here what you are doing, set tree equal to temp. I will explain with an example. See here. Now see here. Yes, root node, you have inserted element 20. Root always points to this node only, and tree is pointing to now. Here, see what you are doing. Tree equal to temp. Tree equal to temp. That means this is a temp node. This is a temp node. Tree equal to temp. That means you are assigning address of temp to tree. Now tree points to this node. Which node? Root node. I hope you understood, students. Now, okay. Now let us see next one. Completed. Okay, completed. First element insertion completed. Now again you need to insert another element. For example, element 30 you need to insert. Where actually 30 will be inserted? 1 second. This is right. This is a data. And this is left, right? Left. 1 second. This is left field, data field, right field. Now let us see. You need to insert element 30. Now where you need to insert element 30. 30 is greater than 20, right? All greater elements must be inserted as right child. How to do it? Let us see with an algorithm, using algorithm. Now see, again you need to call, again same, again you need to call which one? Insert operation. From starting to again it will be executed. Step 1 start, step 2 see, tree equal to null. See, tree is it equal to null? See here, tree is containing address of which node? Node 20. So it is not null. Okay, tree contains address of which node? Tree is pointing to which node? Tree is pointing to node 20. Okay, it is pointing to node 20. It is not null. So this condition will not be, this condition is false. It is not true. When this condition is false, all the statements which are present inside the if will not be executed. Okay, because tree contains address of which node? First node address. It is not null. So this condition is false. When this condition is false, all the elements, all the statements, all these statements inside if block or if body, all these statements will not be executed. Control comes directly to, see here, else if. See the else if. Else if value is less than tree of data. What is a tree of data? Tree of data is nothing but 20. What is value? Value is 30. You are comparing like this. 30 is less than tree of data. Tree is pointing to which node? Node which contains element 20. Tree of data is nothing but 20. 30 is less than 20. True or false? It is false, right? It is false. When it is false, see here, when it is false, control will not go into the if else body. Okay, this statement will not be executed. Now control comes to which part? Else part, because else if condition is false, value is nothing but 30. Tree of data is nothing but 20. 30 less than 20. It is false. When this condition is false, control directly comes to step 4. What is step 4? Tree of right equal to, again you are inserting. See here. Here you are calling recursive function. Tree of right equal to, just wait, I will write here. tree of right equal to, you are inserting in right. See, tree of right equal to insert of tree of right comma value. Again you are passing what, which value? Value means 30. You are passing, 1 second. See, again this function is calling. This is a recursive function. See, again this function is calling. You are calling this function. Again you are calling. Now what you are passing is very important. See here, what you are passing, tree of right. See, initially tree of right contains null. What you are passing? You are passing null. You are passing null and you are assigning to, see, 1 second. You are passing null, tree of right, this one, tree of right is nothing but null. It contains initially null. Null comma 30 you are passing. Now again here function call, recursive call, right? Again from step 1 start. Step 2. What is step 2? Tree equal to null. See, what is a tree? Tree is nothing but you are passing null, right? See, you are passing null. Tree equal to null now. Okay. You are passing null. This is a recursive function. Null equal to null. True. When this is true, what you are doing? You are allocating memory for the node. You are allocating memory for the node using malloc function. You are allocating memory like this. See, like this you are allocating memory. Node will be created using malloc. And you are inserting. Next. What is the node name? Temp. Its node name is temp. Node name is temp. After that, what you are doing in temp data, you are assigning value 30. 30 will be inserted. See here, 30 will be inserted. Next, temp left equal to null, temp right equal to null. Null, 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 null. Completed. Next, see, next. See, if condition is true, right? When if condition is true, else if will not be executed, else part will not be executed. Next, what is executed? Return tree. Now, what is tree? See here, what is tree? 1 second. See, 1 second. I forgot this point. I forgot this point, right? Tree equal to temp. Sorry, I forgot this point. Tree equal to temp. What is temp? This node. Now, tree equal to temp means tree is pointing to which node? 30. Now, tree is which node? 30. The node which contains element 30. Now, see, the else if part will not be executed. Else part will not be executed. Return tree. Return tree means what this is returning? See here. Return, 1 second. Return tree. Now, this address is returned to which node address? See here. See here. See, return tree. This address, which node? 30 node address is returned to tree of right. Now, tree of right contains which node address? The node which contains element 30. Okay. Now see here. See here. 20. Now, this node address is assigned. In this way, you are going to insert each and every element. This is very easy. Just trace it out. Okay, your job is to trace it out. I just explained up to here only, but you need to trace it out. Everything you need to trace it out. Please take an example like previous example. This one. Previously, I have explained this one. Please wait. See, take this example. Take this example and then trace it out. Using this example, trace it out. You will get it. Okay, in this way, each and every node is going to insert. Once again, see this algorithm. At a glance, see the algorithm. Just wait. See, this is the algorithm. Once again, see the algorithm. Once again, see the algorithm. It's very simple. Start. If tree is equal to null, what you need to do? You need to allocate memory for that node and you need to insert value into data field and you need to make left equal to null, right equal to null, and you need to make tree to point to the temp. Temp is a node which you have created. Now you need to make tree to point to temp. Next, if it is not null, or value is less than tree of data. See, value is less than tree of data. Here tree of data is nothing but first node. First node you have created, right? Root node. Here again, if you want to insert another value, that value is compared with the root node element. If it is less than that element, what you need to do? Where you need to insert? You need to insert all lesser elements. You need to insert as left side, left child. So tree of left equal to insert of, again you need to pass a tree of left. This is nothing but null. You are passing null, comma, you are passing next value. Okay. Next, see else part. When this else part will be executed? When value is value is greater. When value is greater, where you need to insert? You need to insert as a right child. So tree of right equal to insert. Again you are calling which function? Recursive function. Same function you are calling. Okay, insert of tree of right comma value. Here tree of right means you are passing null. Remember, you are passing null and you are passing which value? Second value which you are going to insert. You need to return tree. Trace it out. You can understand. If you are not able to understand means in the next class, just ask me, I will explain. Okay, students. Now let us see deletion. How to delete an element. Now let us see deletion. Please practice algorithm. Please trace out the algorithm. Here, remember that in recursive function, here stacks will be used. See, after completion of 4th unit, I will explain how to trace the recursive function. Okay, using stack, I will explain after 4th unit completion. Now, let us see how to delete an element from binary search tree. It's very easy and it's very simple. It's very easy. See here, I will explain it. Here, deletion operation. Keep the heading, student. Deletion operation. What is this? 1 second. Yes, keep the heading deletion operation. And note down the example. 25, 22, 35, 20, 30, 40, 32. Note down deletion operation. Here, there are 3 cases. First case, let us see case 1. I will explain algorithm later. Case 1. Now, if you want to delete an element, which is leaf node, what is leaf node? Which does not contain any children. See the leaf nodes. 20 is a leaf node. 20 does not contain any children. 32 is a leaf node which does not contain any child nodes. 40 is a leaf node which does not contain any child node. What is meant by leaf node? A node which does not contain any children, any child nodes. It is called leaf node. Now, for example, if you want to delete element 40, deleting element 40. If you want to delete element 40, see whether it is a leaf node or not. Case 1, I'm talking about leaf node. If I want to delete a leaf node, see for example 40. If I want to delete element 40, which is a leaf node, simply delete it. Now, the tree will be this one. Simply delete it. If you want to delete leaf node, simply delete it. 20, 30, 32. Yes, see here 40 is deleted, right? Simply delete it. Okay. Just simply delete. If you want to delete a node which is a leaf node, which does not contain any children, if you want to delete it, simply delete it. This is a resultant tree. I hope you understood, students. Now, case 3. Now, 1 second, I will erase this. Case 2. I'm sorry, case 2. Now, case 2. Case 2, let us see it. Next one, just wait. Example 14. Okay, let us see it. Where's it? What is it? Now, let us see if you want to delete case 2. Case 2. Now, if you want to delete an element, for example, let us take 22. See, 22. This one, right? 22. Now, if you want to delete an element, 22. Now, see whether this element has one child or two childs. Two childs. Case 2 is about one child. One child. Now, if the deleted node has only one child, what to do? Case 2 is if the deleted node to be deleted has one child. What you need to do is you need to see here, see 22. 22 has only one child. What is that child? 20 node. If you want to delete element 22, what you need to do is you need to replace element 22 with its child. Okay, see case 2. What is case 2? If the node to be deleted has only one child. Okay, example, I took element 22. If you want to delete element 22, see whether to which case it belongs. It is not a leaf node, right? It is not a leaf node. See, it contains only one child. So if it has only one child, you need to replace that element with which element? With its child, with its child. What is it? 20. Replace the element with see here again I'm drawing. See 25. Now you need to replace the element 22 with its child. What is its child? 20. Like this. 35, 30, 40, 32. This is the resultant tree. I hope you understood, students. Once again, see here, 22 is deleted. See here, 22 is deleted. 22 is deleted and 22 node place is replaced with its child node. What is its child node? Node 20. See here, 22 is deleted and its node is replaced with its child node 20. This is the resultant tree. I hope you understood. Now, case 3. Is it clear, students, up to here? Did you understand case 1 and case 2? Case 1 is nothing but if you want to delete leaf node, simply delete it. If you want to, okay, Haripriya, ma'am, 40 also deleted. Yes, 40 also deleted. Okay, I'm sorry. Yes, 40 also deleted. Okay. Okay. 40 is deleted, right? We have deleted 40 also, right? This is the resultant tree. I'm sorry. Okay, thank you, Haripriya. Now, yes. Now, case 3. Case 3. Case 3. Let us take case 3. I hope you understood case 1 and case 2 is not very easy. Case 1 is leaf node. If you want to delete leaf node, simply delete it. Case 2, if you want to delete a node which has only one child, replace that node with its child. That's all. Now, assume 40 is not deleted. Students, please assume 40 is not deleted. Okay. I'm taking this tree. I'm taking whole tree. I'm taking this whole tree. Now let us see. Assume that 40 is not deleted. Assume that 22 is not deleted. Now, case, yeah, 1 second. Case 3. Let us see case 3. Please listen carefully. Case 3. Later class I will explain algorithm. Case 3. Now see here, case 3 is if deleted node, the node to be deleted. If deleted node to be deleted has two children, what to do? Two children, what to do? Okay, case 1 is if node is leaf node, what to do? You need to delete leaf node. Case 2 is if you want to delete a node which has only one child, what to do? You need to replace that node with its child. That's all. Now case 3, if a node which has two children, you want to delete a node which has two children. For example, let us take 35. Okay, 35 has two children, right? 30 and 40. Assume 40 is not deleted. Okay. Here 35, you want to delete element 35. Here see whether to which case it belongs to. It is not at all a leaf node, and case 2 is only one child. No, it has two childs. So if it has two childs, what to do means you need to replace this node 35 node with its 1 second with 1 second. You need to replace with right subtree. Okay, lesser element in right subtree. Take from right subtree. Okay, lesser element from right subtree. But here see the right subtree, there is only one element. What is that element? 40, right? Replace 35 with 40. See, for example, there is another like this. If there is another elements, here from right subtree, you need to take lesser element and replace 35 with that lesser element. Now, here in right subtree, there is only one element. What is that element? 40, right? Replace 35 with 40. Okay, replace 35 with 40. Here 40 will be, here 40 will not be. Okay, in this way. I hope you understood, students. Any doubts, please respond right now. Now, see here. Mm, see here. 1 second. See this diagram. I'll take this diagram. 1 second. Uh, 1 second, students. See this diagram. Now, I want to delete element 12. I want to delete element 12. See, element 12. See, to which case this element 12 belongs? Here, case 3. Case 1 is leaf node. 12 is not at all a leaf node. And case 2 is, it should have only one child. No, this 12 has two childs. If it has two childs, what to do? Here you need to replace this 12 with the smallest element in right subtree. What is the right subtree of 12? This is the right subtree. In this right subtree, what is the smallest element? 13. Replace 12 with 13. This is the resultant tree. See here. Replace 13, 12 with C, 12. This is you are going to delete 12. Here you need to replace lesser element from right subtree. This is the right subtree. What is the lesser element? 13. Replace with 13. Test completed. This is the resultant tree. I hope you understood, students. Thank you. If there are any doubts, let me know. Any doubts, students? In the next class, I will discuss about the algorithm. I will explain the algorithm. Thank you so much. I hope you understood, students, the deletion and insertion operation of binary search tree. Thank you.